So we have a guy that went fishing, caught a few fish. We're going to take a sample of 3 from the fish that he caught. We want to know how many ways can this sample contain only 1 catfish or only 2 bass. Now once again, the keyword or. So or is the number of A union B. If you don't want to use this formula, the problem is much longer. So we start off with 1 catfish. So we have 4 catfish, pick 1. From the remaining fish, the gar, bass, and sharks, there's 10 of them. We need to pick 2 because our sample wanted to have 3. Plus, or only 2 bass, so combination, 3 choose 2. From the remaining fish, the catfish, gar, and sharks, in other words the ones that are not bass, there's 11. Pick 1. And now we ask, is there any way to get 1 catfish and 2 bass at the same time in this sample? Our sample is going to have 3 in it, so the answer to that is yes. So we subtract off 1 catfish and 2 bass. Notice the last little bit, we 4 choose 1, 3 choose 2, both combinations, and we picked 3 items, so the sample's full. How many 4-digit numbers have, part A says no 7s. Now remember, a 4-digit number starts with a non-zero number, for example like a 3, and then can have any digits after that. So 442 is a perfectly good 4-digit number that meets the category of no 7s. So it's a multiplication principle. Now, I can't start with a 0. I also cannot have a 7 there, so we know there are 10 digits. Take out the 0, take out the 7, that means there are 8 digits remaining. Since I'm dealing with counting numbers, I'm allowed to have repeats. So, of the 10 digits that are available for the second spot, the only digit that's not allowed is the 7, so there's 9 choices there. 9 and then 9. Part B says at least 1 7. Now at least 1 7 has 2 ways to do it. The easiest way to do this is total minus what we don't want. Total would be 9 times 10 times 10 times 10. In other words, how many 4-digit numbers are there? Now what we don't want is all the 4-digit numbers that have 0 7s. Because at least 1 7 is equivalent to saying 1, 2, 3, or 4 7s. So what I don't want is 0 7s. And that was our part A answer, so that is 8 times 9 times 9 times 9. So total minus what we don't want is the easiest way to work that. An exam consists of 6 true-false questions and 5 multiple-choice questions. Each multiple-choice question has 4 possible answers. How many ways can the exam be worked if each question is answered? If we look at our 6 true-false questions, we'll put them in that color. Our multiple choice questions, there's 5 of them. And we start going with this. Well, true false we know has 2 choices for each question. We can think of this as 2 to the power 6. The multiple choice each has 4 possible answers. And that's 4 to the 5th. We're multiplying this together because it's an entire test. It's not a true-false test or a multiple choice test. It's one entire test that contains all these questions, so 2 to the 6th times 4 to the 5th is how many ways we can answer it. The next question says, how many 6-card hands have exactly 3 diamonds, or, once again the keyword or, exactly 3 black cards? So exactly 3 diamonds, we know in a standard deck of cards, there's 13 diamonds, we need 3 of them. And then for the remaining group of cards, so 13 diamonds, that means there's 39 cards that are not diamonds. We need 3 of those, plus exactly 3 black cards. That's the clubs and spades, so combination 26, choose 3, times the things that are not black. Well, that's the red ones, and once again that's combination 26, choose 3. So what we have right here is diamonds, and then other, and then black, and then other. And we need to know now is, well, can we get 3 diamonds and 3 black cards at the same time? Our sample size is 6, so the answer is yes. If our sample was 5, the answer to that would be no, and then we'd be subtracting 0. But since our sample has 6, we need to subtract off the overlap. So 13, 3 times combination 26, 3. That's the 3 diamonds and 3 black cards. Fred has a collection of blocks, 3 red, 4 blue, 5 black. These blocks are brand new, which means they have no scratches, dents, marks in them. In other words, they're identical to each other. All the red are identical to each other, to the other reds. The blues are identical to the blues, and blacks identical to the blacks. We want to know how many ways can Fred place them in a row. One way to do this is to write down 3 letters, the R for the 3 reds, the lowercase b for the 4 blue, the uppercase B for the 5 black. That is one row of those blocks. If I wanted another row, I would shuffle the letters around. You see that's a distinct rearrangement. So we see that this is going to be 12 factorial over 3 factorial, 4 factorial, 5 factorial. Part B says, how many ways can Fred place them in a row if he groups the colors together? Now one thing to realize is that the 3 reds group together. If I shuffle them around, it's still the same 3 reds. Since I can't distinguish between them, I can't tell the difference. So there's really only one way to do the 3 reds all next to each other. The 4 blues, there's only one way for that. And likewise for the black. So really this question boils down to is we have 3 different colors. How many ways can I put the 3 colors in a row? 3 choices for the first color, 2 choices for the next, and then 1 choice for the last, which is in other words 3 factorial. Part C says, how many ways can Fred place the blocks in a row if the red blocks are not next to another red block? Now this sort of goes back to our example in the counting handout 2, number problem 19, that said, how many ways can you put the A's and B's in a row where an A is not next to another A? So we're going to approach it the same way. Now, here's our 4 blue and our 5 black. Now, I've left a little room here so I can put a little vertical line here to represent the placement of the possible spots for the red blocks. So everywhere there's a vertical line, a red block could go. So if I look at these and just sort of number these, we notice that there are 10 possible locations for those red blocks. Now since a red block cannot be next to another red block, I can't reuse one of those slots more than once. Also, the order is not important. In other words, if I pick slot 3, 4, and 5, it's the same thing as picking slot 5, 4, and 3. So I know I have a combination 10, choose 3. Now what that's going to pick is the location for the red blocks. Now the twist in this problem versus problem 19 out of counting handout number 2 is that we have the dividers in essence being blue and black. So now of the blue and the black blocks, how many ways can I put them in a row? Well, that's a distinct rearrangement. We notice there are 9 of those, so 9 factorial there. Divide by 4 factorial, 5 factorial. So the fraction here puts the lowercase b and the uppercase b in a row. Once those are in a row, the red part is placing the red blocks. So together gives me the final answer for part C.